Being able to evaluate a model's performance is one of the best tools we have in our tool set. It can help us determine if the model is capable of meeting our needs or if we need to go back to the drawing board. And as we will see, accuracy many times is not the best predictor of performance. One of the most useful evaluation tools in our arsenal is the confusion matrix. A confusion matrix tabulates all of the correct and incorrect responses a model produces given a set of data. Note that it only works on sets where we have the actual ground truth labels, such as our training, validation, or test sets. The labels on the side correspond to the actual labels in each sample, and the labels on the top correspond to the predicted labels from the model. Let's fill this out using a made-up validation set. The confusion matrix starts out with zeros in all spots. We get the features in the first sample of the set and send them to the trained model. We'll perform a forward pass on those features, and the model will give us which class it thinks those features belong to. Let's say that the model predicts idle for this sample. Because the actual label and predicted label are both idle, we add 1 to the corresponding element. We then move on to the next sample. We send the features of this sample to the model, and this time the model predicts left-right, which is a mistake. So we add 1 to the element that corresponds to an actual label of circle, but a predicted label of left-right. We repeat this process for the third sample in the set, and the model gives us a correct response of circle for the predicted label. So we add 1 to the element corresponding to the actual label of circle and a predicted label of circle. We keep doing this for every sample in the set. If your classifier works pretty well, you might end up with something like this for this made-up validation set of 1,000 samples. A few things to note here. First, all of the elements must add up to be the number of samples used in the set, which would be 1,000 in this case. Right now, we can see that the model is quite good at separating predicting the left-right class when given a left-right example. However, it seems to have a habit of thinking other classes belong to the up-down label. It also struggles some by thinking that many up-down motions belong to the circle class. The confusion matrix alone can help us identify potential problem areas in our model or with our data. Maybe the data isn't good enough, maybe the features don't separate the classes enough, or maybe we need to change the model. All of these would be areas to explore to get a better system. When it comes to model evaluation, we can use the confusion matrix to calculate a number of metrics. Probably the easiest metric to compute is the total system accuracy. To do that, you just sum all of the correct predictions and divide by the total number of samples. In this instance, we have 813 total correct predictions and 1,000 samples, which gives us an accuracy of 0.813, or about 81%. This is a decent classifier, but not a great one. Accuracy is relatively easy to conceptualize, and it gives us one number to use when comparing to other classifiers. However, you can quickly run into problems with it. Let's say we have a naive classifier that always predicts idle as the label. Let's also say we don't have a lot of validation data for our other classes, so our confusion matrix ends up looking like this. This is quite common when working with anomaly detection systems where you aren't able to get many samples of the anomaly class. If we used the accuracy equation as before, we'd see that our classifier is about 97% accurate, which sounds amazing. However, it actually stinks, because it's not even attempting to classify anything. This is why accuracy can be a poor metric for system performance. The confusion matrix alone can help you spot naive classifiers. If your validation or test sets look like this, with all predictions in one class, you likely have a naive classifier. You would want to make some adjustments to your model or collect more data, possibly trying to balance your data sets. There are a number of other metrics we can compute. Before we do, we need to define a few important terms. Many of the calculations using the confusion matrix comes from statistics with a binary classifier. Here, we only have two classes, positive and negative. The positive class might be something like a patient having a particular disease. We collect symptoms from a number of patients and use that to predict if the patients have the disease or not. We sample 100 patients that we know have the disease or not, which is the ground truth, and come up up with this confusion matrix based on our test results. The true positives are the number of people we predicted to have the disease and actually did. The true negatives are the number of people who did not have the disease and we correctly predicted that they did not. In a good classifier, we want the true positives and true negatives to be high compared with the rest of the values. If we predicted positive but the patient did not have the disease, that's a false positive, which is also sometimes called a type 1 error. Similarly, if we predicted negative but the patient did have the disease, that's a false negative. This is sometimes called a type 2 error. These 4 possible outcomes can be used to calculate most of our metrics that help us evaluate a classifier's performance. However, let's first expand this to a multi-class confusion matrix. To compute the true and false positives and negatives for a more than 2 label classifier, you must compute those values separately from the perspective of each class. For example, let's take the idle class as being the positive case. That means all other classes become the negative case. Our true positive case is still when the predicted idle label matches the actual idle label. To get the false positives, we add up all the times the predicted idle label did not match the non-idle actual label. Similarly, for the false negatives, we sum up the times the model predicted idle for the class but missed the mark. Everything else falls into the true negative category from the perspective of the idle class. Separate from the total system accuracy, we can calculate the accuracy for a particular class or label. To do that, we look at our target class as if it were the positive case in a binary classifier. We then take the sum of the true positives and true negatives and divide the result by the total number of samples. In this example, we would have an accuracy of 92.7% for idle as the target class. Next is the true positive rate, which is also called the sensitivity, recall, or hit rate. Here, we find the percentage of predicted target labels out of all the samples that have the ground truth target label. With our medical example, it can be useful to talk about how sensitive a test is at identifying people with the target disease out of everyone who definitely has the disease. The term recall comes from studies on information retrieval. It measures the percentage of results or documents returned out of all the documents that should have been returned. They are both calculated the same way and give us good insights into our classifier system. In this example, we would get a true positive rate of about 84%. Another metric is the true negative rate, which you'll also hear referred to as specificity or selectivity. To calculate it, we sum up all of the true negatives and divide that by the same number of true negatives plus the sum of false positives. This gives us an idea of how good the system is at predicting the non-target class. Continuing with the medical example, this would be the test's ability to reject healthy patients who did not have the disease. A test with high specificity has fewer false positives. In our example here, the system has a true negative rate of about 95.4% for the idle class. You'll also see precision being used alongside the recall metric, and it's sometimes called the positive predictive value. This comes from document retrieval studies and is used to measure the amount of relevant results returned out of the total documents returned. We calculate precision by dividing the true positive number by the sum of the true positives and false positives, which is the total number of cases that the system predicted to have the target label. In this example, our system would have a precision of about 85%. One way to combine the precision and recall into one number is to compute their harmonic mean. This gives us another form of accuracy for our target class. The F1 score is often used when there is a class imbalance where the accuracy metric does not give us what we need. Much like accuracy, it will be a number between 0 and 1. The F1 score of the idle class in our example would be about 0.845. If we compute the F1 score for each of the target labels, we get something like this. I've also added the per class accuracy scores so you can see how the F1 score might be a little different. Note how the accuracy might be a little misleading sometimes, whereas the F1 score gives you a little more information by taking the precision and recall into account. Even using the per class accuracy gives you more information about the system than the total accuracy. You can average or use a weighted averaging scheme to combine the F1 scores if you'd like to describe the total system performance. Note that the F1 score gives equal weight to the precision and recall scores, so if you want one to be more important than the other, you will likely need to look into other scoring systems. Let's go back to our naive classifier. We already found out that it has a total accuracy of 97.3%, which sounds great. Even if you look at the per class accuracy scores, this classifier looks amazing. Things change when you start using the F1 scores, however. Outside of the idle class, the F1 scores are all 0 because precision and recall are both 0. When we average these scores together, it's much lower than the total accuracy. This allows us to catch things like naive classifiers where the accuracy score would mislead us. Note that sometimes accuracy or even the F1 score isn't what you care about. Let's say you're making something that detects possible cancer in X-ray images. In this case, you might be okay with some false positives, but you definitely do not want any false negatives. So you would have to give more weight to something like sensitivity or use different metrics altogether. I hope this has helped give you an understanding of how you can use various metrics and measurements in order to evaluate your model's performance.